Hello, everyone, and welcome to today's webinar, How Can US Policymakers Support the Development of Quantum Computing? My name is Hodan Omar, and I'm a policy analyst at the Center for Data Innovation. And I'm really glad to be able to moderate today's session because quantum computing is coming up more and more in the policy debate and in policy circles around with questions around how can we spur the development of this technology, what are the innovation opportunities, and how and when should we be working with our allies, and when should we be carving out our own competitive advantage in this technology. And to answer some of these questions, we have a really esteemed set of panelists. But before I introduce them, I just want to remind everyone that you can also ask questions of these panelists by submitting questions in Slido. So a quick round of introductions. We have Alison Schwartz, who is the Global Government Relations and Public Affairs Lead at D-Wave. We have Celia Merzbacher, who is the Executive Director of the Quantum Economic Development Consortium, QEDC. We have Christopher Savoy, who is the CEO and co-founder of Zapata Computing. And hopefully we will have Rima joining us soon, Rima Aweed, who is the Commercialization Executive at the Office of Technology Transitions at the Department of Energy. So thank you all very much for joining us. And here's Rima. Hi, Rima. So I just really want to start by setting the stage with what quantum computing is and why it's important for the United States. So Christopher, maybe you could start us off with talking about the different quantum computing architectures that there are, because what you're doing over at Zapata is slightly different from what D-Wave's folks are doing. So what are these different architectures and what are the kind of benefits of this diversity?
Sure. I guess we have to start with this quantum bit, and we're not going to go into the quantum physics of how it works. And actually, how it works isn't really important. It's more about what it does. There is this concept of using, when things get really small, they get really weird, and they do some cool things. This quantum mechanics that's very different from everything that we experience in classical mechanics. Things become weird. So you can have a system in which you have a 1 or a 0, but it's neither. It's kind of like a coin that's flipped in the air that's neither until it lands and you look at it. And so we can make use of that to allow us to process many more numbers than classical mechanics, which is how all normal computers up to now have worked, in a different way. So this process of creating a qubit can be done in a number of different ways. There are different physical ways you can make this thing happen, because lots of things, when they get small, act this way. Electrons act that way, atoms act that way, quantum dots act that way. So there are many different photons act that way. So all of these different small things are able to create these qubits that we can use in quantum computing. So there are many different modalities and ways of creating these qubits that at the end of the day allow us to do this quantum computation. Now, we work on the software, which in some ways is agnostic to which way you do it. So if you use a photon to do a qubit, or you use a superconducting circuit to do a qubit, or you use something else like an ion or a neutral atom to do a qubit, it doesn't matter to us. At the end of the day, it's just a way of getting the superposition 1 and 0 and using all these neat things that allow us to do very powerful computation. But there are some groups working on these technologies. Many of you in the popular press have seen Google with their supremacy experiment that was done using superconducting qubits, and another form of annealing that Allison's company does uses also a superconducting format of qubits, and IBM also uses superconducting. But there are other companies out there, such as IonQ, that use ions, charged atoms to do their work. And then there are neutral atom companies like Code Quanta or Misha Lukin's work at Harvard and MIT that was announced recently use neutral atoms. So there are many, many different types of physical architectures, but they all in some way or another try to create this qubit that allows us to do these computations. They all have different advantages. Superconductors are very fast. So if you need lots and lots and lots of calculations, they're quite quick at doing that. Their operation speed is maybe 1,000 times faster than, say, ions are because of the technology that they're doing. But they are, at least now, a little less accurate than the ions and the neutral atoms are in their calculations. So if you need very accurate results, maybe the ions are a better answer, and they're also better connected. But if you need lots and lots of samples for your algorithm, the superconductors may be better. So it's a very nuanced, sounds very complicated, it is. it's very difficult for a user to know, without a little bit of expertise on the hardware, which of these hardware systems today is better for their particular algorithm or their particular application. In the future, when all of these become what we call fault tolerant or corrected or fully error corrected, that will tend to merge. So it won't matter as much to the programmer. But for today, it really does matter which one you're using for different applications.
Do you think that researchers know ahead of time, how best to figure out which kind of architecture would be best for them?
Actually, benchmarking these against each other is very difficult. The providers of these machines will give you numbers, but that's like saying we have 400 horsepower. Well, yes, but 400 horsepower in a pickup truck is different from 400 horsepower in a sports car. So they're not really apples to apples types of comparisons. And as a matter of fact, there's a call out by DARPA right now to industry and industry consortiums to explore how we might actually do application benchmarking for various things like chemistry and optimization, machine learning, various types of things at that application level to actually answer those questions. So the real answer is researchers don't know. Even the people in the field don't really know from one to the other. And proprietary companies are not so willing always to give all of the comparisons apple to apple to what they're doing. They're always, of course, going to be incentivized to tout the better parts of what they're doing and show the champion data of what they can do. As opposed to compare directly. But this is the reason why DARPA is getting involved here and saying we do need these benchmarks, because government and industry need to know, as users of the technology, which of these platforms are good for which things.
Celia, do you have anything to add? I know that you at QEDC have been doing a lot of thinking about benchmarking.
Yes, thank you. And thanks for the opportunity to be on the panel. QEDC is indeed a consortium of stakeholders from kind of across the whole innovation ecosystem. And we've brought together a representative group from the quantum computing community to look at how to agree upon ways to measure progress. And individual companies can use those to see how they're advancing, as well as users being able to use these kinds of benchmarks and metrics to see how different architectures or different machines from different companies perform for different problems. So it's still kind of early stage to come up even with good ways to assess and measure and compare. So as Christopher said, there's a lot of work going on at different levels. QEDC is working at sort of a very practical level and is working to implement a set of algorithms that they could make public later this year, perhaps, and allow users to start exploring and testing how different systems work on different types of problems.
Yeah, like Christopher said, a lot of this is very technical, very difficult to understand. So Rima, I know that one of the most interesting applications is in energy, and that your office is doing a lot of work to find and support the commercialization of quantum computing applications in energy. So could you talk a little bit about that?
Yes, no, absolutely. And I just want to say off the bat, my office is working with all the program offices, and obviously with the Office of Science as well on various commercialization activities, including quantum. And so one of the areas that we've talked a little bit about in the past, where we see some opportunity is optimization, right? There's combinatorial optimization opportunities, and we know that quantum computers will be able to do that work, and we also see quantum annealing being able to do that work, right? And so we see this as an opportunity to do some early applications, and we're exploring ways that we'll be able to do that. Again, working with the program offices and working with the Office of Science, but this is it's kind of an exciting uncharted field. So we're trying to figure out what's the best way to approach it. And we're working very closely, obviously, with QEDC and a lot of the members there to brainstorm on some of the ways that we could approach some of these things.
I was reading that one of those applications is grid optimization. How is quantum helping in that, quantum computing?
Well, we know that in grid optimization, there's just so much that's happening there right now, where we're trying to integrate so many different types of assets into the grid. And so the grid, historically, has been, it hasn't changed much, right? In 100 years, it's been a spoken wheel type model where energy is created in one place and is distributed out. But that's not working anymore. Things are changing quite a bit, and we've got distributed energy resources that are spread all over the place. And so we see the grid evolving to a place where it works more like a network, almost like the internet, or like the human brain, for example, where there's so many different areas where power can be sourced, and it could flow two ways. And so the idea is the grid would need to be able to remain balanced and be able to decide and transact dynamically electrons that are going both ways, essentially, right? And that all needs to be figured out. And it's a mathematical problem, one that we think that quantum computing will be able to help solve, because this is the type of dynamic decision making that's going to be required is going to be very, very extreme at some point. And that's not to say that classical computing can't help, and that we're not going to explore hybrid models and that they wouldn't work in conjunction. But these are things that we're still figuring out. And so the question really becomes, how dynamic do we want the grid to be? How many assets do we want to be able to integrate with the grid? So when I say distributed energy resources, I'm not just talking about solar panels and wind farms, right? I'm also talking about your electric vehicle that could be bidirectional. We're talking about your refrigerator, there are water heaters, things that we have in our home that are assets that could also communicate with the grid. And these are millions and millions and millions of intersection points that in theory could be managed. We would like to manage them. And some of this is already happening, and we're trying to aggregate these things at nodal levels or at the building level. But eventually, this becomes very complex, and I know that it gives the grid operators pause, but if we have some solutions, a platform where all that can intersect and be figured out and optimized, right? Which is where we see the quantum capabilities coming into play, then we see an opportunity to really modernize the grid, make it more resilient, make it more reliable, and actually create value for many different types of people, because the people who have that car that's intersecting to the grid could actually extract value from that as well. And so it's a win-win. The utility doesn't have to build a new generation plant, and the person who buys a car has now a dual purpose for that vehicle, that electric vehicle. And so it's exciting times, I think.
Yeah, thank you. Like Alison, like Rima says, a lot of this value creation is happening now, but oftentimes, at least I find, oftentimes in the policy conversation, quantum computing is framed primarily around the national security aspect, the long-term national security threats, which are large. But what do you think are the kind of economic and social rationales today?
Thanks so much for the question. Really appreciate it. So I actually want to pull on something that both Christopher and Rima said. Not every problem is going to be right for every quantum computing hardware system. And Rima mentioned something called hybrid. And we actually think that over the next probably 8 years, while the quantum hardware continues to advance to the next generation, you're kind of in this world of hybrid where you get the best of both the classical computational as well as the quantum computing, whether it be on a gate model or an annealer or topological or on the different types of qubits that Christopher was mentioning. There's some really interesting and exciting things that are happening today. So Hoden mentioned that you're talking about national security issues and encryption and what are you going to do post quantum for encryption. But there's work in drug discovery right now. We opened up our platform for free for anybody working on COVID, and we had over 280 folks come in to build applications, and one of which, Menton AI, was doing protein folding, and they're now in wet labs testing for drug discovery. We had other companies that were coming in and using it for autonomous vehicles talking to each other in a more efficient and effective manner. They were doing it specifically in the use case of a manufacturing floor because they couldn't have as many people on the manufacturing floor because of COVID. So how can you actually drive efficiencies? Other folks are now using it for other manufacturing purposes. Volkswagen is looking at a paint shop optimization where they found 80% reduction in waste because of using a quantum application. There's emergency response. How are you going to get resources to the right places? Get them, if you're in the deep south or out west with the wildfires and hurricanes, minutes and hours are critically important. So how do you get the resources there to help people faster? Those are kind of the social and economic areas that we can do things in a more optimized way, maybe do things in a brand new way through different applications that are being developed, both from the software side as well as with some of the hardware folks.
Thanks. Celia, while a lot of this is happening, it's still early days, and it seems to me that there are two broad sets of activities that are supporting the development of quantum computing in this innovation process. There's the public sector and the private sector, both doing different kind of complementary activities. What do you kind of see as the role of each, and what do policymakers need to consider to ensure that the overall supply chain is working?
Thanks. That's a very good question. As you point out, there's a lot of activity going on in various parts of the supply chain. So on the public sector side, the government investments do tend to focus on early stage research and research infrastructure, and sort of making available what's needed in order to do the scientific advancements. The Department of Energy has set up a number of research centers that are multi-institutional and involve the national labs and so on. So that's where the government focus tends to be in terms of the investment. The private sector is working really hard to come up with products and make things that are going to be useful and to build a business. So those activities, but it's very early stage. And so there's a natural sort of adjacency to these two sets of activities, and the different parts of the ecosystem, the innovation supply chain, need to be in communication so that the results of the research move efficiently into the people who can develop it and incorporate it into their products and services. And the people who are doing the practical application work need to, that effort and what their needs are needs to be known to the researchers so that they can also focus where their efforts are needed most in a way. So QEDC sits at that intersection to a certain extent. We are an industry-driven organization that has the mission to enable and grow the quantum industry. But at this point in time, in order for that to happen, that means making the industry connections back to the research pipeline. And so we have such broad engagement across the supply chains and ecosystem that it's a logical place for the research communities to kind of come and find those connections. So that's a really important part of what we do. Now, I will say that the supply chain also could be interpreted to mean all of the enabling technologies that are needed in order for the system developers, the people who are building quantum computers, to be able to build those systems. And that involves a lot of non-quantum or classical technologies like lasers and control electronics and cryogenic cooling technologies and so on. And we may talk about that more later, but that part of the supply chain is predominantly supplied, in many parts of it anyhow, by relatively small companies that don't have enormous research budgets and offices and departments. And so the capacity of those organizations to do the research that's needed, because they built up their business to serve not the quantum community, but other communities often. They build lasers for telecommunications, or they build cryogenic systems for the research, the physics research community, or the high energy physics system developers. So the commercial off-the-shelf products aren't there, and there is a real opportunity, if the US wants to keep those supply chains here, for policymakers to step in at this stage and make some targeted investments, or think about ways of making sure that those small companies have what it takes to be able to supply the quantum industry going forward. There's just not a big enough market to sort of to drive it, in the private sector alone right now.
In terms of those enabling technologies like cryogenics and lasers, what do you see as the kind of high level gaps, not just in terms of the size of the firm, but where they are? Because as I understand it, a lot of cryogenics is happening in the UK. Is there a gap in the US? What should the US kind of be doing?
I think that there's quantum expertise and capabilities in some amazing firms all around the world. And so there's a sort of natural global marketplace and supply chain that already exists. But indeed, if it's sort of critical to these systems, the US wants to make the part of that supply chain that's in the US as strong as possible. So I think there's no reason to sort of not be participating in cryogenics, for example. To your question about sort of what are the high-level gaps, I think that there's a sort of general gap in commercially available technologies that are designed for quantum purpose. And so companies, one of the system developer companies that's a member of QEDC said their approach is buy it and try it. So they buy something that's commercially available. It wasn't specified or verified that it would work in the conditions they were going to use it. And then they try it and see if it will work in that environment, perhaps at low temperatures or in certain regimes that, again, it wasn't sort of specified to work. And so what's needed now is for standards and for the suppliers to address those needs and not leave it to the developers to have to test everything themselves, or in some cases just make their own because the commercial version is not available at all. And so those are, across many of the enabling technology areas, I think, problems that are going to need to be addressed. And it's still, as I said, it's still very much a research. The biggest customers are still researchers almost, even if they're researchers in big companies that are doing the R&D for commercial applications. Is still often at the research stage. And so there's a sort of market that exists today, but there's a bigger market in the future, and figuring out how to be prepared for that and incentivize the work that needs to be done to intersect that future market is, I think, an important policy question.
Thank you. Christopher, just to dive into something else that Celia said in terms of the ecosystem, one of the other really key players is academia. Many of the most successful quantum computing companies and startups today, like Zapata, are university spin-outs. How can policymakers make sure that the companies and the research that's coming out of universities and out of academia is oriented towards the highest value add sectors of economic activity, things like manufacturing, renewable energy, transportation?
I think you have to really back up and look at what the motivations are for research institutions and what research is. Research versus development. We talk about R&D. Commercial entities really should be doing more D than R, more development of something useful, as Celia was saying, something more near term. Research needs to happen, and primarily really for the purpose of developing the next generation of scientists and engineers capable of knowing how to work these systems and developing the next generation of theory. I think where research and development and government policy can really help in this way, if you want to aim things towards something that will be practical and will give, at the end of the day, the United States a geopolitical advantage over competitors. It's a fierce competitive environment out there. And in other countries, there's less of a we don't want to pick winners allergy in policymaking, I think, out there. So, I think we need to look back in our own history at examples like the Apollo project, because we need government, I think, to generate things that are more near term and real. I love what's happening in the DOE projects and whatnot, but it's about high energy physics that will help the DOE labs with their mandates. It's not about how to help the Commerce Department, for example, help with infrastructure or the grid or these types of things for the most part. If you look at, I'm on one of the boards of one of the projects there, and most of the applications being discussed are things like esoteric field theory, or black hole edge conditions, or these kind of things that are very hard to do on a classical computer, but aren't necessarily practical. As opposed to, if you look at the Apollo project, that was government as a customer saying, we want a semiconductor-based computer to go with the lunar lander to the moon. The Fairchild semiconductor that went up there was not fault tolerant. It didn't work perfectly. And in fact, it wasn't trusted by mission control in Houston. The IBM mainframes did all the work, and it was just used as a backup, except for one section when it went to the dark side of the moon. But it worked, and it created an entire industry, and it created Silicon Valley. So because there was an actual practical thing that you were doing with government as a customer. We can look even further back in history with electromechanical computers and census counting. In the 1800s, that was used to generate the whole idea of using electromechanical computers. So there was a government use to do something that was difficult to do with the current state of technology, and government became the first customer, if you will, to have academics and industry focused. For example, Fairchild worked with MIT in that project to focus industry and academics towards creating more practical, more near-term outcomes. And we can see that China, our adversary in a lot of ways, is doing that. And they have very near-term commercial outcomes for government and for industry that they're putting in place that incentivize people to move towards more near-term commercial things. So I think we can do better at being more near-term focused. Not that we don't want to do the further out things that will be nice theory papers and get you a Nature paper. That's very important. But I think that some piece of the budget, a greater piece of the budget, has to be government as a customer in other areas of government where we have problems that need to be solved by this, that can provide a benefit for society in climate change, in areas of infrastructure, things that are completely bipartisan, where we can get the academics and industry to actually use these computers for something near term that will create academic value and really catalyze the whole development of an industry, just like it did with Silicon Valley and the Fairchild example.
Alison, what are some of those examples of government as a customer? How can they use it for, say, optimization? And Christopher touched on infrastructure. What are the kind of options there?
No, thank you so much. I actually love where Chris was going with this because, you know, when we're looking at quantum computing, when you Google it, most people say it's not ready. It'll be 15, 20 years out. And they talk about encryption, as you had mentioned, Hoden, the national security side. But there's so much that can be done with the current state of the technology today through these hybrid solvers and hybrid algorithms. So when you're looking at infrastructure, you have everything from the traditional roads, bridges, airports, rails. There's a company in Italy that's actually using it to look at where to put the mobile wireless network in a more optimized way. You have folks that are using it for how to optimize traffic flow. As you're doing it, Volkswagen actually worked with D-Wave systems in Lisbon for busing routes. You also can do it on rails, and Australia just announced that they're looking at quantum applications for optimizing the rail network. You had the Australian military looking at it for last mile resupply and logistics, and can they find, by using quantum computing applications, a more optimized way for doing those last mile resupply. And they were actually also looking at it, not just in that, but in using autonomous vehicles for that, or drones. And they found that a quantum application where a classical computer could solve a really easy problem, like 4 trucks going to 3 places. The problem you have is when it got to be 20 trucks or 100 trucks going to 200 places, that problem was too big for a classical computer to solve at all, yet a hybrid application could solve that. And so there's a lot of those that are very important and things that I think it's exciting for Congress and policymakers and Department of Energy to kind of lean in and see how they can help.
Rima, still thinking about the federal government, the German government has recently kind of supported the creation of a consortium that's going to develop, trial, and share quantum computing applications. Do you think that if the federal government was able to have some kind of platform or way to share the quantum computing applications that different agencies, come up with, that would help or be useful in any way?
Yes, and we are working towards that. I want to point out that we at the DOE in particular, we have test beds that we provide access to, and with the additional work that's being done at the QIS centers, that provides us an opportunity to provide additional space for test beds, and we want people to be able to play around and be able to develop algorithms. But at the same time, we also want to work with industry, right? Because industry is a co-developer. They help us build out and consider the use cases, and they're ultimately, and people in industry will also be customers, as well as the federal government, as we can imagine, right? And so we've done a lot of this type of work in the high performance computing space, and so we will obviously be doing that as well in the quantum computing space. But we also want to work in conjunction with industry and be thoughtful about, what is our role versus what is industry's role. And we don't want to, and I think, part of the struggle is figuring out what is federal role versus industry role, because we want industry to be viable, right? The role of government is to tackle a problem and then gracefully bow out, right? I joke, my job is to talk myself out of a job. That's the goal here, right? We want industry to take the reins and move things forward. And so we are trying to be thoughtful about addressing problems where industry can't address a problem. So kind of to Chris's point, like, why are we focusing on these high particle physics things? This is where the basic science program focuses on. But that's not to say that we can't look at more practical applications within the program space, because the DOE has the applied programs and we have the basic science program, and they're totally different focus areas, right? But that's and so my office is trying to serve as a bridge between them to incentivize and inspire the connections, right? And this is why I've been talking about grid optimization, because obviously I me personally, I can't speak for the entire department, but it's not to say that we're not talking to our colleagues about the idea that what is being developed in the basic science space there's some aspects of it that could start to be commercialized, and we just want to help de-risk that to the extent possible, so that then the private sector could pick up where we leave off and take it further, and so that they're viable. And then I also just want to mention that we do have the National Quantum Coordination Office within the White House. That's part of the Office of Science and Technology Policy. That is also coordinating and organizing all the various federal agencies that are invested in looking at quantum to talk and coordinate, and we do that on a regular basis. And so we will continue doing that and figuring out how to better interact with the private sector.
Thank you, Celia. Do you have something to add?
I did. I just wanted to mention a very specific example of a proposal that's moving forward for the government to help in this regard, and that is a program called QUEST, the Quantum User Expansion for Science and Technology program, where some government funds would be made available to researchers who want to propose projects that involve using cloud-based quantum computing resources, like the ones at D-Wave, involving software that might be from Zapata, and from all the US quantum computing suppliers. So having a portal where researchers can go and figure out if the problems they're working on are amenable to being approached using a quantum computer. And right now, there's a sort of, you're preaching to the choir to some extent. There's a physics community, there's a community that knows about quantum computing and knows that they can go to D-Wave or to Google or IBM or Honeywell or one of the other platforms and get access perhaps and use those systems. But there are people doing all kinds of other problems and research, from biomedical research to economic research and other areas, that perhaps don't know how a quantum computer might help them. And so by creating a program where you're encouraging researchers of all kinds, and even from the private sector, to get access to the quantum computing resources in order to address their problems is going to accelerate progress on the hardware side and the software side, on the researcher's side, and often students are the ones who actually do the research, so they're going to be getting hands-on experience at the same time. So it's a really win-win-win kind of idea that I think is going forward, and we're excited to see it implemented, hopefully.
Just to follow up on that point, you know, incentivizing researchers to kind of use quantum computing is on the one side, but the other side is talent and making sure that you have this pipeline of people who have the knowledge to be able to use these tools. To what extent do you think that the kind of existing workforce is able to, or that there are kind of initiatives to ensure that the existing workforce, as opposed to the future workforce, have the tools that they need to use these systems?
That's a great question, and I'd love to also hear from the folks who are, you know, in the companies having to struggle with access to the right people, and for that matter, at the government agencies. But so there's a mismatch between supply and demand today. There's no question about that. Over time, I think it will come to equilibrium, and there will be a natural increase in the supply side, but that takes time. And so this is a really important question. And I think that there, of course, are resources online, and people who want to go take an online course from one of those that are available today can do that. But I think there should be easy access, or awareness should be made widely available, so that someone who is in the middle of their career, or you know, a recent graduate and already out in a job or in the scientific and engineering community knows where to go. And that's everything from educational institutions that may have postgraduate options, sort of compact executive-based programs and so on, to professional societies and other institutions that traditionally do professional development work. But quantum doesn't fit into one discipline. And so there isn't going to be a single professional organization that can do this job. And it really does need to be a sort of all hands on deck approach among the various educational pieces of the system.
I'd like to ask you all, really. Alison, do you have thoughts on how you're finding it at D-Wave?
Sure. Celia is correct. I mean, for us, finding talent is critically important. And a lot of the folks that we end up hiring, we actually have to train because they don't understand quantum computing. They know how to code in Python, but they don't know how to code an algorithm that maps back to the D-Wave systems. Or we can't find folks who are have the expertise in superconducting chip fabrication or cryogenics. And I know there's work going on through QEDC, through the National Quantum Initiative at DOE on K through 12 education. But as Celia mentioned, there is a real need for, it's not just about physics, it's computer science, it's algorithm development, it's getting to those folks that are in the business optimization analytics programs, because they're going to look at things from a practical perspective, connecting them in with the physics side, connecting folks in with the next generation of chip technology and hardware technology. And looking at that, not just K through 12, but also kind of what can universities do within their master's programs and postdoctoral programs today. And so that's something that we at D-Wave are very excited about and leaning in as much as possible. And I know Christopher also has leaned in on that one. So I'm going to pass it over to him to talk a little bit about it as well, because getting that talent is just critically important. And we as companies can't wait for 15 years for a person that's in elementary school or middle school to be able to come into the workforce today.
Yeah, I think that, you know, building pipeline, when you say K through 12, there's already a, you know, Q through 12 program that some of you may be aware of. You know, for policymakers, you know, when we're on the Hill with Celia, the first question they said, what can we do in kindergarten? Well, yeah, that is where you start, but I'm sorry, we cannot wait, to Allison's point, 12, 15, 20 some years for a PhD to emerge out of kindergarten. We're going to lose if we have that kind of mindset geopolitically. For policymakers, they need to know that this is a critical need. It's a need now. I'm excited about some of the programs. You know, the University of Wisconsin, I think, was one of the first to offer a master's degree. So you don't have to go all the way through and get a PhD in an esoteric area, but have an applied master's degree in quantum computing. And my alma mater, the University of Rhode Island, is announcing a program. It's actually starting this fall, and there'll be a big inaugural conference for it in October that Alice and I are both involved in supporting, to create a master's program. And they've got great young faculty being recruited to that program to produce people who don't have to wait 7 years of a PhD program from their bachelor degree on to become productive in the industry. And I think this is natural. I'm old enough to remember when, you know, computer science was mostly applied mathematics. There wasn't really a computer science degree. And I think that now there's enough of a need realized by industry that we need to have a more of an applied track for people. And it's hard to do because you have to have a bit of physics, a lot of physics, actually, a lot of mathematics, and a lot of computer science. And it's tough to create a program that does all of those things. But that's really what's needed. And we actually really are, you know, in a supply rut right now with the people we need. And that's just going to create, you know, a talent war that I think really creates a problem for all of industry, because then the prices go up. It's really hard to get enough people to really move the industry forward in a way. And then you add on to all of that the existing problem. I'm very glad that I'm the only male on this call, but this is not, please audience, don't think that this is the status quo out there. It's not. Gender and other diversity wise, we are in a hole. In STEM in general, but then when you combine quantum computing, which is physics and math, you get into even a more difficult situation. So we have to work harder on that at the graduate school level, at the pipeline building level very much. And I think, you know, the QEDC and the Workforce Development Act has some initiatives in there and that we care about very much as part of pushing forward, because we're going to have to work to not exacerbate that problem for the industry as well.
Can I just compliment what Christopher said? Because we did do a survey actually of our membership to ask what positions do you see filling in the next 5 years or so, and what skills and degrees would you expect the people you hire or would you want them to have? And interestingly, more than half of the jobs did not require a PhD necessarily. And many of the skills that were sought did not say quantum. So they wanted software engineers, they wanted people who knew optics and photonics. And so while having a quantum, if you're a student and you looked at these data, these, you know, list of knowledge, you would say, okay, I've got my electrical engineering degree. If I just go take one course that gives me some of this quantum knowledge, that would just round out the set of skills in a way that would make you very competitive. So you don't necessarily need a deep expertise. Certainly companies would like to have, you know, the perfect match, but everybody has to do some education and on-the-job training. And so the fundamental skills are going to be really important and useful. And I think with just a little bit of tweaking, an individual student can really make themselves, you know, stand out and succeed and be able to enter and flourish in a career in quantum computing.
Thank you. Rima, do you have kind of a governmental perspective? Because I also assume that you needed kind of a deep understanding of grid optimization or the grid or kind of clean energy in general. So what is your take on this?
Yeah, so this reminds me of a conversation I previously had where we talked about the types of people that are going to be needed in quantum, and the takeaway was it's all hands on deck, right? We need all types of people to take interest in work in quantum. And as Celia said, there's ways you can go about rounding yourself out despite your background. And I just off the bat, I'm a quantum enthusiast, not a quantum physicist, right? So clearly there's ways to be relevant and add value if the drive and passion and interest is there. And so from the government perspective, we're obviously through the labs, we have a lot of PhDs, we have a lot of posts, and and a lot of the work that we're doing helps to enable people achieving their postdocs and meeting their requirements to get their degrees. And so, but people coming in aren't always necessarily quantum physicists, right? And we've got a lot of engineers that are on board as well that are working alongside our physicists to build these quantum computers and networks. But we also need to be sure that we can bridge what they're doing with what the applied programs are doing, right? And that's a different skill set, as you mentioned, understanding, for example, the grid, right? Understanding how the grid works. And so these are different types of people with different backgrounds, but I don't think we're necessarily looking to have someone that has all of those capabilities in one person. What we need to do is create an opportunity where people with these various backgrounds can talk and collaborate and brainstorm. And that's what we're trying to do. We're trying to create an environment where that brainstorming and that cross-fertilization is happening. And organizations like QEDC is doing things like that too, right? Like when we go to these meetings, there's people with all different types of backgrounds that are part of these advisory committee discussions, and it's been incredibly fruitful because you get all these different perspectives, and together we think through problems and have these aha moments. And so, on the government side, we very much are trying to bring people to the table to talk and collaborate that have totally different backgrounds, but we have a shared mission, and in that we both want to solve a problem, and working together, we're able to do that. So,
thanks. Taking a little bit of a step back and looking globally, and also turning to some of the audience questions. Alison, the UK has launched, and we've also talked a little bit about, cloud resources. The UK has got this quantum computing as a service that they've recently launched that is a commercial kind of industry-led, I think, effort. And I think the Canadian government is working on something similar. How do these tools support the adoption of quantum computing, and how does it really differ than what we were talking about earlier with the Quest bill?
I think that it's really interesting to look at what's happening globally in this effort, specifically these quantum as a service kind of focus. So this is getting to where Christopher was talking about earlier, of those near-term applications. What can we develop, whether it's for agriculture or sustainability? There was some work in Japan on waste collection, and can we reduce CO2 emissions at the same time while collecting the same amount of waste? So there's environmental issues that can come up with that. So I think that the Quest program is a great option. There's also in the US Competes Act a call out for near-term applications. There's work that could be done right now in the Presidential Quantum Advisory Council. They can create a working group to look at near-term applications and figure out, how do we help manufacturers, logistics? How do you help with drug discovery, transportation, infrastructure, broadband rollout, emergency response, as I had mentioned before? There's so many different areas that we can kind of lean in. And the US right now hasn't stepped in, and we're seeing other global folks step in. The interesting thing was there was a presidential advisory committee on communications resiliency that came out from DHS, the NSTAC report in May, and they actually called about creating a test bed and creating a quantum sandbox where you could create some of these things for communications resiliency. Those things, along with Quest, I think are going to be really interesting if the US kind of steps up to lead there.
Thank you. And looking at what people should do, I think it's also a good time to look at perhaps what people shouldn't do, because the EU has this kind of controversial plan to exclude the United Kingdom, Israel, and Switzerland from collaborative research projects on novel quantum technologies. So Christopher, I wanted to ask what you thought of this. What impact do you think this will have on kind of EU innovation in this space and generally competitiveness?
Yeah, I mean, we talked about the talent pipeline. I'll just start there, and how you need to get these people they're not a dime a dozen people who have these quantum capabilities at a company like ours to be able to do the work, and they're global. And with COVID, it's made it harder, but you can't necessarily relocate everyone anywhere. I find it near impossible to get one of my best developers is in the Democratic Republic of the Congo. We can't get a visa to get that person to Canada or the United States. So what am I going to do if there's an export control thing? Fire that person? That would be horrible for U.S. industry. So we have to think globally. The global workforce is global. And I think that, if we get too far on the policy side into, export control, and we do these exclusionary things, both on a workforce level or on a company level or a technology sharing level or research and development supply chain level, we could have the law of unintended consequences really come back to bite us very quickly. So I think we need to think and do some futurizing and thinking with policy community to really think what would those unintended consequences be if we were to retract and be less global. Because with the QEDC work, I know that we set out through the steering committee and through all of our work to state very clearly that we're about global supply chain. We just want everyone to play by the same fair rules for IP and for IP protection, and playing not using this in nefarious ways, for example. But those things, I think, can be done with a light touch in policy and through working with our partners to make sure that we're aligned in our collective policy making. I think it really creates a difficulty if we're going to cut out specific countries or different groups of countries and really lock into these cliques because the people just aren't there. And I include our adversaries. The academic work that's being done in China is immense, and it's really contributing. What are we going to do? Shut that down and not let them publish to the archive? That would be crazy. So we really have to think of how do we best have these standards and rules that in a free society that we would like to uphold and live by the rule of law, how can we best have those things happen in a global supply chain for a technology that will help all of humanity? I really firmly believe that. So how do we get those benefits, realizing that there are nation state actors who have nefarious purposes behind them and are not aligned? It's a really tough Gordian knot of problems to solve, but I don't think that the knee-jerk reaction to slip into geopolitical silos is really going to help us. And I think it may set us back, and I don't think overall that it will help us compete because of this talent actually being distributed globally.
Celia, what have we actually done? Because I understand that we are working with Japan, or the United States is working with Japan. Are there any other agreements that the United States has made? Are there opportunities, distilling what Christopher said down into actually implementing these steps?
Well, yes, there was a statement that was signed between the U.S. and Japan sort of right before COVID shut down travel and made it much more difficult to do sort of diplomatic work. So I think that there's been a slowing of the ability to build on that kind of agreement, but there's still an interest in doing so. I want to just sort of remind everyone that I'm not a government agent or a government agency. We get some funding from the government, but we're really outside government. I know that, and Rima may be able to speak to a recent arrangement that was set up between DOE and the Japanese agency that does energy, NEXT, and energy research. So there are some steps, and that called out quantum as an area where they wanted to collaborate. We had just yesterday actually a roundtable with the Netherlands, between the US industry and the Netherlands, to talk about opportunities for collaboration in anticipation of when QEDC does open to non-US membership. So our approach, unlike the one you described in the EU of sort of defining countries and regions that were allowed or not allowed, QEDC's approach, and Christopher alluded to it, is to establish principles and say we welcome those who abide by these principles. We do have procedures for reviewing applicants, and getting those in place is taking some time. But eventually we hope to be able to welcome people from all around the world who are participating in the quantum community and ecosystem, as long as they abide by those norms. And so we're hoping that that kind of approach actually promotes people doing the right thing and being able to participate.
Rima, what do you see as the kind of international opportunities to cooperate with strategic allies?
Well, I will say, Celia had mentioned the discussions with Japan. We also, through the quantum centers via the labs, also they too have collaborations and partnerships that they're establishing internationally. So, for example, Fermilab has a partnership with INFN. They coordinate. It's a coordinating institution for nuclear particle theoretical and astroparticle physics. So the labs themselves are able to have these types of relationships. So it doesn't necessarily have to be just at the DOE level or just at the agency level, but they can also partner through our labs, which are an extension of the federal government. And that tends to be a little easier, generally speaking, because they can sort of hone in on something specific that they want to work on. So I just see more opportunity for that type of collaboration. And again, it's probably even quicker and easier to do it via the national labs, which is where a lot of this QIS work is taking place.
Thank you. We have just a couple of minutes left, and I feel like we've covered a lot in this conversation: benchmarking, use cases, talent, access to resources like the cloud. So I wanted to ask each of you as kind of like a final thought, what you think should be one of the top priorities that US policymakers should be considering and really kind of moving forward on to ensure that the development of quantum computing in the United States. And I'll start with you, Christopher.
Yeah, as I think I'd just be re-emphasizing that we need some greater percentage of the budget to be aimed at shorter term results that are actually practical. Yeah, we still need to do the R&D, that's great, but it's a very minuscule share of the current federal budget that's being aimed at near term results-oriented uses of quantum computing. And I'd love to see policymakers start thinking about those outcomes because that will drive industry and it'll create a virtuous cycle that'll feed back into research and research collaborations. And we really need that, just like we did in the creation of Fairchild and Silicon Valley.
Alison?
I echo Christopher. I think that we are doing a great job on the long-term research. I think that there's been a really big focus on that, and the national labs have really kind of taken that on. I think the next leg is what can be done with the technology in the near term. That's actually the biggest question we hear from customers is, but what can we do with this? And so being able to answer that, whether it's through grand challenges that come out of NIST and Commerce, or it's a actual working group that's developing kind of what are those public-private partnerships for near-term applications to tackle some major problems like sustainability, grid resilience, communications resilience, rolling out for broadband. I mean, we're all in our homes because of COVID and trying to figure out, how do we navigate this? How do we actually help those parts of the community in the US that actually don't have broadband, that aren't able to connect in remotely, and being able to find an employee in the Congo that is your most valuable person, and yet, you can't get them to be in your office. So I think that it's an and leaning in on QEDC and other kind of consortiums that bring the whole community together. We've been talking a lot about quantum computing, but the quantum industry is really big, from sensing to lasers, and we've talked about other stuff. So being able to look at things kind of across the whole board and looking at all the different technologies.
Rima?
I agree that there's opportunity to do more. There always is, right? And obviously DOE is spending a lot of time and money via the QIS centers to do the R&D work, to answer and tackle some of the harder pieces, to actually develop the quantum computer and look at applications that can have profound effects, but are obviously really hard problems to solve and require looking into deep space and other things like that, right? But at the same time, there, at least within DOE, there's a cohort that is looking at some of the more viable use cases, some of the shorter term wins that are possible, that fit within our mission space, right? And being the Department of Energy, we can look at things that relate to energy. And so, and that's what we're doing. And this effort has been, there's been work on quantum at the federal level for some time, but DOE has started working on this in the last few years, with a lot of emphasis and with significant funding. And I think we're off to a great start. And I think that there's a lot more to come in terms of, building out the R&D piece, but also looking at some of the more applicable areas that we've started discussing just recently.
And last but not least, Celia.
I'll take just 30 seconds and shine a light, especially on the small companies. Innovation really happens in startups and small businesses in this country. And we have a number of tools in the toolbox, like the SBIR program, that can be deployed towards supporting those organizations. Our membership is 80% small companies. And so figuring out from a policy perspective how to help those companies get the investment and the resources that they need to succeed, I think is really important. Thanks.
Thank you so much. That's right on the hour. So thank you everyone for joining us, and thank you to all the great panelists.
Thanks so much.
Thank you.
Thank you.